Hi, I'm Paul. We are doing Leetcode must-know interview questions. Today's challenge, evaluate division. The rating is medium. I hope you don't get a question like this at a coding interview. I think I think the rating should be hard, but if you want to say it's medium, it's at least at the top range of medium. Well, anyway, here's the challenge. You are given let me read it first. You are given an array of variable pairs, equations, and an array of real numbers, values, where equations at I equals AI BI, and values at I represents the equation AI divided by BI equals values at I. Each AI or BI is a string that represents a single variable. This is not going to make any sense without examples. First of all, let's scoot this over so we can see what the method signature looks like. All right, calc equations. We are going to get a list of string lists, a list of strings, equations. Each of the inner list here will have two variables. The variables will be represented as lowercase letters. Then you've got another array, double. Values. Now the values represent the result of evaluating a division on the equations. And finally, we have a list of queries. Each query is also a two-element list containing variables, lowercase letters, and based on the equations and the values that we've already been given, the challenge is to evaluate the queries. And we'll look at an example of it. I want to see, is it a good idea to look at the example now, or is it a good idea to go through this? You are also given some queries. I think I already said that. Return the answers to all queries. If you can't determine the answer to a query, return -1. The input is always valid. Assume that queries will not result in division by 0 and that there is no contradiction. Not sure what that means. The variables, note, variables that do not occur in the list of equations. So in other words, if a query has a variable that does not occur in the list of equations, then that variable is undefined and answer cannot be determined. All right, so here's an example of what this is going to look like. See which one of these is actually the best one to look at. All right, let's do this one. And actually, first, let me say that let's look at the topics on this. It's a lot of topics. The important topics here, I think, are union find and graph. All right, so we can do this as a graph algorithm using union find. I have to say that I don't find the union find algorithm to be all that intuitive. Well, I mean, at a high level, it's really simple, but my explanation of it, keep in mind that I don't consider it, the implementation of it is complex in my opinion. All right, so union find is used on disjoint sets. A disjoint set means sets that have no elements in common. So here's our equations in example 1. AB and BC. initially, and each of those will be a graph element. Initially, they are disjoint sets. A is a set, B is a set, C is a set, and we're going to union them. So eventually they'll wind up in the same set. So each variable you can think of as a node in a graph, and each equation is an edge that connects two variables. The value associated with each equation, which is in the values array, is the weight of the corresponding edge. So then the problem of finding the ratio of two variables becomes a problem of finding a path between two nodes in the graph. And if there is a direct path between the nodes, representing, now we get to the equations, representing the queries, I should say, the queries. If there is a direct path between the numerator and denominator in a query, we can calculate the result. If there is not a direct path, or one of the variables doesn't exist in the graph, we can't calculate it, and we'll have to return -1. So to find connections and calculate ratios, we can use a union find. The union, so there's two operations. Union will connect two disjoint sets, the union the two sets, and find, if you can do find on an element and find out what set, if any, that element occurs in. Let's talk about the general solution approach. There are data structures that we use in union find, so we're going to have to set those up. We are going to union the nodes, in this example A, B, and C, based on the equations that were given. And then we're going to go through the queries. So if we can find both variables in our graph, they're in the, and they belong to the same connected component, we can calculate the solution, we can calculate the ratio using the weights along the path that connects the variables. Otherwise, it's -1. So, let's see, maybe I can draw this here. Wait, where is it? Oh, I see. All right. So let's say we have A, we have B, we have C. All right. Now, the edges between these nodes represent the ratio of the node to its parent. All right, so we can see the first equation, A, B, has a value of 2. So we put a 2 here, okay? Second equation, the ratio of B to C is 3, all right? If you want to think of it another way, you can see that one of the queries is BA. So what's the value of B over A? Well, you do it in reverse. The ratio of B to A would be 1/2. Now, the union find algorithm that we're using, it's going to use path compression, where instead of a long path of nodes, all the nodes that are connected, all the nodes in the same set, are going to point to a single root. So what it's actually going to look like is, and another thing I should say here is the ratio. If you want to do a ratio from A to C, now that's also in the queries, A and C, the answer being 6. So what is the ratio of A to C? Well, if the ratio of A to B is 2 and B to C is 3, then the ratio of A to C is 6. We can calculate that. With path compression, it would look like this. We would have C as the root, we would have A, and we would have B. Now, A to C would be 6. B to C would still be 3. And what else do we have here in the queries? Yeah, and the ratio of any node to itself is 1. That's also in the query. We have A over A, which yields a value of 1. So that's how union find works, and let's take a look at an implementation. All right, so I noticed that it took so long to talk through the union find that I don't want to take the time to type the whole thing out. So I typed it. I haven't tried to run it yet, but I'm going to try to walk through it. And again, to me, it's a complex algorithm to implement. So I'll do the best I can with it. But we've got these are data structures that we use in union find: a parent map and a weight map. The parent map maps each node to its parent node. And if you're using path compression, it maps each node to it's going to eventually map each node to the same node. So if we have equations like this, where is it? That's example 3. Where's example 1 again? Like AB, BC. All right, so B is going to be the parent of A, C is going to be the parent of B, but as I said, we're not going to do a long path of nodes. Everything is going to point to C. So A will point to C, B will point to C, C will point to C. All right, here is the weight. Again, that is the ratio of each node to its parent node. Initially, A to B is, let's get that over and see it. You can see the value here. A to B is 2, B to C is 3. Eventually, C will be the root of everything. And so B to C is still 3, but A to C will be 6. All right. Initialize the, well, create the maps, initialize the maps. Next, perform union operations. All right, so we look at each equation. We get the variables for each equation. In this case, the first one is A and B. Find the, well, okay, now we'll look at the find. But the find right now, every node is just a parent of itself. Okay? So, the parent of A is A. The parent of B is B. Are those equal? No. So in that case, set the parent of A to B and set the weight. The weight in this case is going to calculate out to 2, which is the value that was provided in the values array. All right, next equation is B and C. We'll get B and C. Find the parent. Again, B and C are just parents of themselves. If they are not equal, set the parent of B to C and set the weight. In this case, the weight is going to be the ratio of B to C, which is 3. All right, I think everything now is set up and we can start looking at the queries. So yeah, queries.size, we need an array for the answers that we are going to return. This method returns an array of doubles. That's the answers. All right, so if we go through this, let's see, queries. All right, varsity queries, get the variables from the first query, and they are A and C. If we got to make sure that they are in the parent array, meaning that we've seen them as part of the equation, and we've seen A, we've seen B. They are part of the same, set. They both have a common root, which is C. So we do this. We get the var C divided by var D. So that's, yeah, the ratios. We do the computation based on the ratios. Let's take a quick look at find. I guess the interesting thing in here would just be the path compression. That is, if an object has a parent other than itself, then we get that, and we do a recursive find on the parent, meaning if A's parent is B, rather than just setting the parent of A to be B, we find the parent of B. Parent of B is C, so then we set the parent of A to C. So that's path compression. Eventually, all the nodes in a set are pointing to the same root. Now, in doing that, we have to adjust the weights. So, for example, when I first drew this, A to B was 2, B to C was 3. If we're going to make C the parent of A, we've got to do an adjustment. We've got to make the ratio of A to C 6. So that's what's going on here in the find. And all right, well, at this point, let's try and run it. Oh my God. I can't believe that ran the first try. All right. So that's the base cases. Let's try and submit the whole thing. Hmm. 1 millisecond. Okay. Yeah, so that's it. 1 millisecond, 2 milliseconds. I don't know. You can do this without path compression, but there isn't a wide range of results here on the timing. I mean, maybe this is the non-path compression algorithms. Anyway, that is an example of union find, the union find algorithm for evaluate division. Hope you enjoyed it. And feel free to like, subscribe, comment, and see you next time.